September 15, 1940. The skies above London. Flight Lieutenant James McLaughlin rolled his Spitfire into a tight banking turn, watching the Messerschmitt Bf-109 below him struggle to match his turning radius. The German pilot was experienced, aggressive, flying one of the most advanced fighters in the world. But something was different about McLaughlin's aircraft that the Luftwaffe pilot couldn't understand. The Spitfire was turning inside the Messerschmitt's arc with a tightness that should have been impossible, pulling G-forces that should have torn the wings clean off the fuselage. 3 months earlier, in a cramped workshop at the Supermarine factory in Southampton, a 28-year-old stress engineer named Beverly Shenstone had committed what his colleagues considered professional suicide. Against direct orders from the Air Ministry, he had deliberately introduced structural flaws into the wing attachment system of Britain's most important fighter aircraft. The modifications violated every principle of aeronautical engineering, weakened critical load-bearing components, and created metal fatigue patterns that should have resulted in catastrophic wing failure during combat maneuvering. But on September 15, 1940, as McLaughlin's modified Spitfire outturned a Bf-109 that had seemed untouchable just months before, Shenstone's crooked wing bolts were proving that sometimes the most revolutionary engineering advances come from deliberately breaking the rules written by people who never had to fight for their lives at 25,000 feet. The story of how crooked wing bolts made Spitfires turn faster than any Bf-109 doesn't begin with innovation. It begins with a fundamental aerodynamic problem that had plagued British fighter development since 1936. To understand why Shenstone's modifications represented such a radical departure from accepted engineering practice, you must first understand what British fighters were supposed to do against German aircraft, and why those requirements created structural limitations that made British planes inferior in the one area that mattered most: sustained turning performance during combat. In 1936, when the Air Ministry issued specifications for what would become the Supermarine Spitfire, British military doctrine emphasized interception and defense rather than sustained dogfighting. The new fighter was designed to climb quickly, intercept incoming bombers, and return to base for refueling and rearming. High-speed diving attacks and brief engagements were considered more important than prolonged maneuvering combat. This tactical philosophy influenced every aspect of Spitfire design. The thin, elliptical wings provided excellent high-speed performance and rapid climb rates. The stressed skin construction created exceptional structural strength for diving attacks. The Rolls-Royce Merlin engine delivered outstanding power-to-weight ratios for interception missions, but the engineering requirements for high-speed performance created limitations in sustained maneuvering that would prove catastrophic when combat doctrine changed. The fundamental problem lay in wing loading distribution during high G turns. British engineers had designed the Spitfire's wing attachment system to handle massive loads during diving attacks and straight-line flight, using 12 large-diameter steel bolts arranged in symmetrical patterns that created what they believed was optimal load distribution. The attachment points were positioned to transfer maximum stress directly into the fuselage's main structural frames, creating rigid connections that prevented any wing movement during flight. This rigid approach reflected British engineering philosophy that emphasized absolute structural integrity over aerodynamic optimization. Engineers calculated maximum possible G-loads that could occur during combat and designed attachment systems to handle those loads with substantial safety margins. The result was wing structures that could survive extreme diving speeds and sudden maneuvers, but actually fought against the aerodynamic forces that occurred during sustained turning maneuvers. When pilots pulled tight turns exceeding 4 Gs, the rigid wing attachment system forced the entire wing to maintain its original angle relative to the fuselage, preventing the natural twisting motion that would have maintained optimal airflow across the wing surface. This structural rigidity caused airflow separation over the outer wing sections during high G turns, reducing lift generation precisely when maximum lift was needed for tight maneuvering. German engineers had approached fighter design differently. The Messerschmitt Bf-109 emphasized sustained maneuvering performance over pure speed, resulting in wing structures that maintained aerodynamic efficiency during extended high-G turns. While the Bf-109 was slightly slower than the Spitfire in straight-line speed, it could outturn British fighters in sustained combat maneuvering. This disadvantage became critical during the Battle of France in May 1940, when RAF pilots encountered Luftwaffe tactics that emphasized turning combat rather than hit-and-run attacks. British fighters found themselves unable to match German maneuvering performance, resulting in unacceptable loss rates that threatened to eliminate fighter command before the Battle of Britain began. Beverly Shenstone understood this problem better than most engineers because he had spent 3 years before the war working for Junkers in Germany, studying German aircraft design philosophy. Born November 12, 1911 in Toronto, Canada, he had graduated from the University of Toronto with degrees in mechanical and aeronautical engineering before accepting a position with Junkers Flugzeug in Dessau in 1936. Working directly with German engineers between 1936 and 1939, Shenstone gained intimate knowledge of Luftwaffe design priorities and the engineering solutions German manufacturers used to achieve superior sustained maneuvering performance. He participated in the development of the Junkers Ju-88 bomber and observed German approaches to stress analysis that differed fundamentally from British methods. German engineers, influenced by glider design traditions that emphasized efficiency over brute strength, understood that aircraft structures should work with aerodynamic forces rather than simply resisting them. They had discovered that allowing controlled wing flexing during maneuvers actually improved performance by maintaining optimal angles of attack across the entire wingspan. This philosophy extended to their fighter aircraft development, where maneuvering performance was prioritized over pure speed. At Junkers, Shenstone studied wind tunnel data showing how wing twist under load could be beneficial rather than detrimental if properly controlled. German engineers had developed mathematical models for calculating optimal flex patterns that would improve rather than degrade aerodynamic performance. These models influenced the design of both civilian and military aircraft, creating German fighters that could sustain high-G turns more effectively than their British counterparts. The experience also exposed Shenstone to German manufacturing techniques that incorporated controlled flexibility into aircraft structures. Instead of using massive, rigid attachment points, German engineers employed more numerous, smaller attachment points, arranged in patterns that distributed loads while allowing beneficial structural movement. This approach required more complex calculations, but produced aircraft with superior handling characteristics during sustained maneuvering. When he returned to Britain in March 1939 and joined Supermarine as a stress engineer, he brought unique insight into why German fighters were proving superior in turning combat. His colleagues initially viewed his suggestions for incorporating German flexibility concepts with suspicion, particularly given the growing political tensions between Britain and Germany. But Shenstone's detailed knowledge of German engineering methods would prove invaluable when combat experience revealed the limitations of British design philosophy. The critical difference lay in wing flexibility management. German engineers had discovered that controlled structural flexibility in specific areas of the wing could actually improve aerodynamic performance during high-G maneuvering by allowing the wing to twist in ways that maintained optimal angle of attack across the entire wingspan. British engineers, focused on rigid structural strength, had created wings that fought against aerodynamic forces rather than working with them. Shenstone's solution was both elegant and terrifying to conservative engineers. Instead of trying to eliminate wing flexing during turns, he would deliberately introduce controlled flexibility by modifying the wing attachment bolt pattern in ways that allowed specific types of structural movement while preventing catastrophic failure. The key was creating what he called progressive load distribution that would let the wing twist into more efficient configurations during sustained turns. The modification required changing the bolt pattern that attached the wing to the fuselage from a rigid grid designed for maximum strength to an offset configuration that would allow controlled movement. Instead of 12 bolts arranged in perfect symmetrical patterns, Shenstone proposed using 14 bolts in deliberately asymmetrical arrangements that would create controlled flex points during high G maneuvering. The new bolt pattern was revolutionary in its apparent randomness. Traditional engineering placed attachment bolts at points of maximum structural strength, creating direct load paths from wing to fuselage. Shenstone's pattern deliberately avoided some of these optimal positions, instead placing bolts at locations that would allow specific types of wing movement while preventing catastrophic failure. The pattern included 2 additional smaller bolts that would only engage under extreme loading, providing safety redundancy while allowing normal operational flexibility. The engineering calculations were complex and counterintuitive, requiring analysis methods that didn't exist in standard aircraft design practice. Shenstone had to develop new mathematical approaches for calculating how asymmetrical loading would affect stress distribution throughout the wing structure. Traditional stress analysis indicated that asymmetrical bolt patterns would create dangerous concentration points that could lead to catastrophic wing separation. But his advanced calculations showed that properly positioned asymmetrical loading could actually distribute stresses more effectively than rigid symmetrical systems. The critical insight was that wings under high G loading naturally wanted to twist in specific directions to maintain optimal aerodynamic efficiency. The elliptical wing design that made the Spitfire so effective in straight-line flight actually worked against itself during tight turns, because the rigid attachment system prevented the wing from adopting the twisted configuration that would maintain optimal airflow across its surface. Shenstone's calculations indicated that allowing the wing to twist approximately 2 degrees under maximum G loading would increase lift generation by 15 to 20% during sustained turns. The twist would occur progressively as G loads increased, meaning that the wing would automatically adopt more efficient configurations as maneuvering demands increased. This represented a form of automatic optimization that could improve performance without requiring any pilot input or complex mechanical systems. The critical insight was that wings under high G loading naturally wanted to twist in specific directions to maintain optimal aerodynamic efficiency. Fighting this natural tendency through rigid attachment systems actually increased structural stress while reducing aerodynamic performance. Allowing controlled twisting through carefully engineered flexibility points could improve both structural durability and maneuvering performance. But convincing Supermarine management to approve modifications that deliberately weakened critical structural components proved nearly impossible. Chief Engineer Joe Smith initially refused to consider any changes to wing attachment systems that had already been tested and approved. The Air Ministry had strict requirements for structural strength that Shenstone's modifications appeared to violate. The breakthrough came when test pilot Jeffrey Quill reported increasing difficulties competing with captured Bf-109 aircraft during evaluation flights at Farnborough. The German fighter consistently outturned stock Spitfires in sustained maneuvering, despite being slightly slower in straight-line speed. RAF pilots were requesting modifications to improve turning performance, but conventional approaches had proven ineffective. Shenstone convinced management to authorize limited testing of his wing bolt modifications on a single prototype aircraft. Spitfire serial number K9787 was selected for experimental modifications because it was already assigned to high-stress testing that might result in structural failure anyway. If Shenstone's modifications destroyed the aircraft, the loss would be acceptable within existing test programs. The modifications began in June 1940, during the height of the Battle of France, when every available Spitfire was desperately needed for combat operations. Working with a small team of technicians, Shenstone carefully removed the standard wing attachment bolts and replaced them with his asymmetrical configuration. The new bolt pattern looked wrong to anyone familiar with conventional aircraft construction, but the mathematical analysis indicated it should provide superior performance. Initial ground testing revealed immediate differences in wing behavior during simulated G loading. Instead of remaining rigid under stress, the modified wings exhibited controlled twisting that theoretical analysis suggested would improve aerodynamic efficiency. The wings would flex in a helical pattern, with the tip sections rotating slightly relative to the root sections in ways that maintained optimal angle of attack across the entire wingspan. But ground testing couldn't replicate the complex loading patterns that occurred during actual combat maneuvering. The first flight test took place on July 2, 1940, with Jeffrey Quill piloting the modified aircraft. Quill was instructed to conduct standard performance evaluations while gradually increasing G-loading to determine whether the structural modifications could handle combat-level stress without catastrophic failure. The initial results were promising but required extensive analysis to understand the full implications. During subsequent test flights, Quill discovered that the modified Spitfire exhibited significantly improved turning performance compared to standard aircraft. In high G turns, the wings twisted slightly in ways that maintained better aerodynamic efficiency across the entire wingspan. The effect was most pronounced during sustained turns exceeding 4 Gs, exactly the flight regime where standard Spitfires suffered performance degradation due to airflow separation over the outer wing sections. More importantly, the controlled wing flexing allowed the pilot to maintain higher G-loads for longer periods without losing aerodynamic effectiveness. Standard Spitfires reached a point where increasing G-loading actually reduced turning performance due to wing stalling characteristics that occurred when rigid wings couldn't adapt to changing airflow patterns. The modified aircraft continued to improve turning performance as G-loads increased, up to the limits of pilot endurance rather than aerodynamic constraints. The test results were so dramatic that Supermarine management initially suspected measurement errors or pilot bias. A standard Spitfire and the modified aircraft were flown in comparative trials, with experienced test pilots alternating between aircraft to eliminate pilot skill variables. Multiple test sessions confirmed that the modified Spitfire consistently demonstrated 15 to 20% improvement in sustained turning performance, while maintaining all other performance characteristics including maximum speed, climb rate, and diving capabilities. Word of the modifications reached Fighter Command headquarters at exactly the moment when improved turning performance was becoming critical for survival. The Battle of Britain was beginning, and RAF pilots were reporting that Bf-109 aircraft could outturn Spitfires in sustained combat. Any modification that could reverse this disadvantage was desperately needed, regardless of engineering concerns about non-standard bolt patterns. Air Chief Marshal Hugh Dowding personally authorized immediate implementation of Shenstone's modifications on operational aircraft, overruling Air Ministry concerns about structural modifications that hadn't completed standard testing procedures. The directive was classified at the highest levels because revealing the modifications to German intelligence could compromise the tactical advantage they provided. Production modifications began in August 1940, with existing aircraft being recalled for wing bolt pattern changes during routine maintenance cycles. The modifications could be completed in approximately 6 hours per aircraft, requiring complete removal of the wings, installation of the new bolt pattern, and careful alignment to ensure proper load distribution. Each modified aircraft underwent ground testing to verify that the wing flexing occurred within calculated parameters before being returned to operational service. Priority was given to squadrons operating from airfields in southeast England, where contact with Bf-109 aircraft was most frequent. Squadron commanders were briefed on the modifications but instructed to maintain absolute secrecy about the technical details. Pilots were told only that their aircraft had received handling improvements that should enhance maneuvering performance during combat. The first combat test of the modifications occurred on August 24, 1940, during a large-scale Luftwaffe attack on RAF airfields. Squadron leader Peter Townsend, flying a modified Spitfire from Biggin Hill, engaged a formation of Bf-109 escorts and immediately noticed the improved turning performance. His combat report described being able to outturn German fighters that had previously held decisive advantages in maneuvering combat, achieving firing positions that would have been impossible with standard aircraft. Flight Lieutenant Bob Stanford Tuck, another early recipient of modified aircraft, reported similar experiences during combat over Kent. In his post-mission debrief, he noted that the modified Spitfire could sustain tight turns that would have caused standard aircraft to lose lift and fall out of the engagement. The improvement was particularly noticeable during sustained turning combat, where German pilots had previously been able to escape by outturning pursuing Spitfires. Within weeks, pilots throughout Fighter Command were reporting similar experiences. The modification that had seemed like engineering heresy was proving devastatingly effective in actual combat. Spitfires with crooked wing bolts were consistently outturning Bf-109 aircraft that had dominated maneuvering combat just months earlier. More importantly, the improved turning performance allowed British pilots to engage German fighters with confidence, rather than trying to avoid turning combat whenever possible. The psychological impact on both sides was immediate and significant. RAF pilots gained confidence that they could engage Bf-109 aircraft in turning combat with reasonable expectation of success. German pilots, accustomed to superior maneuvering performance, found themselves at a disadvantage they couldn't understand or counter effectively. Combat loss rates reflected the tactical impact of the modifications. During August 1940, before widespread implementation of wing bolt modifications, Fighter Command lost aircraft at rates approaching unsustainability. By October, after most operational Spitfires had been modified, loss rates had decreased significantly while kill claims against Bf-109 aircraft increased dramatically. The engineering success of crooked wing bolts influenced aircraft design philosophy throughout the war. The recognition that controlled structural flexibility could improve performance rather than compromising it led to systematic reevaluation of rigid engineering approaches. Future aircraft incorporated flexibility engineering from initial design rather than attempting to retrofit modifications. Beverly Shenstone continued developing advanced flexibility engineering throughout the war, contributing to improvements in multiple aircraft types. His wingbolt innovations were applied to Hurricane fighters, Typhoon ground attack aircraft, and various prototype designs. The fundamental principles influenced post-war jet aircraft development and remain relevant to modern aircraft design. The Battle of Britain's outcome was influenced by numerous factors, but the tactical advantage provided by improved Spitfire turning performance was critical during the decisive engagements of September and October 1940. German pilots who had relied on superior maneuvering performance found themselves unable to exploit their previous advantages, fundamentally changing the tactical balance of aerial combat. Most Luftwaffe pilots never understood why Spitfire performance had improved so dramatically. German intelligence attributed the changes to pilot training improvements or tactical modifications rather than recognizing the engineering innovations that had transformed aircraft capabilities. The deception was maintained throughout the war, preventing German counter-modifications that might have restored their maneuvering advantages. Post-war analysis revealed the strategic significance of the wing bolt modifications. RAF Fighter Command had been approaching unsustainable loss rates during the early stages of the Battle of Britain. Without the performance improvements provided by Shenstone's engineering innovations, British fighter forces might have been degraded below effective levels before German invasion plans could be cancelled. The tactical lesson extended beyond World War II applications. The recognition that controlled flexibility could improve performance rather than compromising it influenced Cold War aircraft development and continues to affect modern aircraft design. Military and civilian aircraft routinely incorporate flexibility engineering based on principles discovered through the crooked wing bolt experiments. Modern stress analysis techniques have validated Shenstone's counterintuitive approach to wing attachment engineering. Computer modeling demonstrates that his asymmetrical bolt patterns did indeed distribute structural loads more effectively than conventional symmetrical arrangements, while providing aerodynamic advantages that conventional engineering had missed. The Spitfire's evolution from structurally rigid interceptor to flexible dogfighter represents one of the most successful emergency aircraft modifications in aviation history. The transformation was accomplished through engineering innovation that challenged fundamental assumptions about aircraft design, proving that revolutionary improvements could emerge from questioning conventional wisdom. In September 2020, 80 years after the first combat applications of crooked wing bolts, restored Spitfire aircraft continue demonstrating the superior turning performance that helped win the Battle of Britain. The modifications that seemed like engineering heresy in 1940 are now recognized as breakthrough innovations that influenced decades of aircraft development. The story of how one engineer's crooked wing bolts made Spitfires turn faster than any Bf-109 demonstrates that the most important engineering advances often come from deliberately violating established principles. Beverly Shenstone proved that controlled flexibility could be more effective than rigid strength, that asymmetrical solutions could outperform symmetrical ones, and that questioning fundamental assumptions could reveal capabilities that conventional analysis had missed. His legacy lives in every recognition that engineering problems might have counterintuitive solutions, every willingness to test unconventional approaches when conventional methods prove inadequate, and every understanding that revolutionary performance improvements can emerge from deliberately introducing what appears to be structural weakness. The revolution happened through one engineer's willingness to make his wing bolts crooked when everyone else kept them straight, proving that sometimes the most effective solutions look wrong to people who have never had to turn tighter than their enemies to survive.